Has Mother Nature helped in the cleanup from the BP Deepwater Horizon accident and oil spill? Welcome to a special edition of the News Hub. I'm Kelsey Hubbard, and joining me here is the Wall Street Journal's Lee Holtz. Thanks so much for being here.
Always a pleasure.
And also joining us from the University of California in Santa Barbara is microbiologist David Valentine. David, thank you so much for joining us. And you know, when a lot of us were watching those pictures of oil sludge pouring out from the accident site in the Gulf of Mexico, many people didn't realize how much methane gas had been released, and a new report published in the journal Science shows that actually naturally occurring microbes have basically eaten up or consumed much of that. Tell us about the report and how that happened.
Yeah, it was not common knowledge at the time, watching all those videos, that a significant proportion, 20% or so, of everything that was emanating from that ruptured well was methane gas. That methane gas, it emanated into the deep ocean waters, and it was trapped at water depths of about 3,500 feet and below that. And that methane was then subject to the movement of the currents, and it moved away from that site. When we were there in June, and we published a paper in the journal Science some months ago on this, we found that the methane was abundant and that the bacteria were not touching the methane. They were not consuming it at that time.
Oh, okay, I'm going to jump in here. When you say you saw it in June, the background levels, if I remember our conversation, were tens of thousands of times higher than the normal background. Yet when you went back in September, you found almost nothing. I mean, that's an extraordinary gap. What happened in there?
Yeah, that's exactly right. In June, the levels were more than 100,000 times the normal background level in that depth region. When we came back in August, September, October, we did not find any methane whatsoever at all beyond the background levels. And instead, what we found were slight depletions in oxygen that spread over a couple hundred miles of length and some tens of miles of width. And in those same regions where that oxygen was gone, was missing, were the bacteria that normally consume methane. Sort of like the cat that ate the canary, sitting there by an empty canary cage with a feather sticking out of its mouth.
But David, just a simple question here. The Gulf of Mexico obviously is huge, and this was a sort of, I guess, cloud or plume of methane gas you were testing. How do you know you got the right spot? And maybe it just didn't drift to the left or the right, and you just didn't throw the measurement over the side of the boat in the right area? I mean, it sounds like a maybe silly question to you, but I think a lot of people out there might be wondering, are you sure that the testing levels were right?
Yeah, it's not a silly question, and this is something that we had to address from day one when we started seeing that there was no methane in these samples. We went to 207 different locations in the Gulf, and there's constraints because of where the seafloor is, that these waters, because of their depth, they could not have gone north and they could not have gone east, which basically leaves west and south. And so what we did is by going to these 207 different locations, we looked for the telltale signatures of the oil and of the microbial activity that came from the Deepwater Horizon spill that we had seen with the methane in June. And so we used indicators of residual oil to help us guide our sampling efforts. And that the residual oil that we would measure in real time aboard the ship was always occurring with these sags in oxygen that are indicative of the respiration of hydrocarbons in this layer. Very much the same as we saw in June, except now it's over a much broader area. So we covered on the order of 400 or 500 kilometers of distance, and we every time we ran into these indicators, this oxygen loss and this fluorescence from the oil, this indicator of oil, we would go until it stopped, and then we'd keep going a bit to make sure that we didn't miss any patches. So we covered quite a bit of the Gulf of Mexico, and in addition, the models that have been developed based on where the currents are going indicate that that's the way that all of this plume was moving.
Okay,
so,
and I'm sorry, David, you were also able to actually detect slightly elevated levels of these naturally occurring methane-consuming microbes. But now I'm told that they're almost impossible to culture in a laboratory. So, I mean, how do you actually detect them? How do you find them?
So we collect water samples and we filter out the bacteria from the water sample so we can concentrate the bacteria. We then extract the DNA from the bacteria, and we go through a series of steps that allows us to sequence the DNA of the bacteria that are present. From that sequence, we can analyze the community of bacteria that's existing there, and there are certain telltale markers that indicate methane consumers. And those markers were present in these waters in September, whereas they were not present back in June.
And David, or Lee too, I'd love to ask, where do we go from here with this? Does this give us any insight into how we can respond to future oil spills, knowing that these microbes are so great at eating up a lot of the toxicity? And also, does it give us any insight into global warming and how that works, especially if these microbes are naturally occurring?
Mm-hmm.
So the bacteria that consume methane do not consume the other compounds that are present in oil. And so one of the difficulties of understanding the microbial response to a deep oil spill is that each compound is consumed at a different rate, and many of them by different bacteria. It's not a simple story. The methane story we have well in hand, and methane is important in this case because it was so abundant and there were concerns about oxygen drawdown, but it doesn't say anything about the more toxic compounds that were in the oil, such as the aromatic hydrocarbons. Now, on the climate front, this is an interesting forbidden experiment that was performed, in that there are natural releases of methane that have occurred throughout geologic history, and this methane emanates from the deep ocean, and it's thought to have impacted climate. There are concerns that this could also happen in the future, and this experiment that was performed for us on an industrial scale, it emitted on the order of 200,000 tons of methane into the ocean, and it provides an opportunity for us as scientists to ask, what happens to methane when it's released into the ocean in this manner? So what it tells us is that Mother Nature does have the capacity to consume methane on the matter of a couple of months when it's released into the deep ocean in large amounts.
So methane under the sea floor is a not uncommon thing around the continental margins around the world. These, I guess they call them methyl hydrates. Now, if these ever thawed and released, you're suggesting there's a possibility that these bacteria might act as a kind of a safety valve. But, there are reports now that in the Arctic, for instance, that methane is starting to leak up from some of these thawing deposits, and there doesn't seem to be any evidence of microbes doing us any good there. Is temperature a factor here? I mean, what's the issue?
The issue is going to be one of the depth, and along the margins of the continents, the methane hydrates are located at depths of about 500 to 600 meters and below, and that's water depth of 500 to 600 meters, or about 1,500 feet. In the Arctic, the situation is different because the sea level used to be about 400 feet lower, some 20,000 years ago. As a result, there's permafrost that is underlying the ocean today, and the methane hydrates are trapped under the permafrost. And so as that permafrost thaws, it's occurring in shallow water, and that methane has an opportunity to make it directly to the atmosphere in the bubble form without ever dissolving. Methane has to dissolve into the water in order for the bacteria to access it. So if the methane can't dissolve, bacteria can't get it. That's not to say that there is not an important role for the methane oxidizing bacteria in the Arctic system, and it simply hasn't been explored yet.
This may take care of the methane in the Gulf of Mexico, but are there other bacteria at work on other toxic byproducts from the spill that you've been studying?
Yeah, the answer to that is probably, and this particular study does not address those compounds in oil, but we have been using measurements of oil to help us track where the plumes went, and there is still some residual amount of oil in the water. It's been diluted dramatically compared to what it was during times of active flow, but there's still oil there, and we also see bacteria in our water samples that appear to be oil degraders. So those organisms are still there. There's still some oil there, and I would assume, based on those two pieces of evidence, that there are still some active bacteria there eating some of the oil components.
All right, fascinating stuff. Thank you, gentlemen, both for joining me. Lee Holtz here from the Wall Street Journal. You can read more about his story on WSJ.com. And David Valentine from the University of California in Santa Barbara. Thank you for your time.
Yeah, thank you, David.
Thank you very much.
That's a special edition of the News Hub. I'm Kelsey Hubbard in New York.